Everything in the world that you can see, feel, and touch is made of matter. From water under a bridge, to the air you breathe, to that special someone's hand that you get to hold. But we've known since 1932 that antimatter exists. It's sort of like the opposite of matter. Except, in this case, opposites are best not to attract, because when matter and antimatter come together, they annihilate each other, exploding in a cataclysmic shower of heat and light. So, when a team of researchers from multiple institutions around the world actually found a form of helium atoms with both matter and antimatter mixed together, they knew something big was going on. Today, we'll explore what happened in this experiment and why it's so important. Let's go into the impossible. A new set of data hints that new physics may be just around the corner. Stick around and I'll explain how. I'm Brian Keating, an experimental physicist and cosmologist at UC San Diego. I love doing experiments in the lab and working with the most brilliant people from around the world. And I like to bring to you an experimentalist perspective. So what's going on with this anomalous antimatter? Helium, as you know, is the second most populous element in the universe, making up about 24% of the baryonic or ordinary matter in the universe. It was formed right after the Big Bang. It was formed from protons, themselves made of normal matter. Helium nucleus is an atom's center with 2 protons and 2 neutrons. The protons give it a positive charge. To counterbalance and keep these 2 positive like charges together, you also need neutrons, whose strong force opposites cause the proton and neutron to stick together and allow 2 protons to stick together. Now, electrons in the outer orbitals are the negatively charged particles that give the overall atom its neutral charge. Namely, the 2 positive charge in the proton plus the 2 negative charge of the electron gives a net charge of 0. The neutrons, spoiler alert, are electrically neutral. Now, the antimatter equivalent to the proton is known as an antiproton. It's the opposite of a proton. The opposite of an electron is called a positron. So where a proton has positive charge, an antiproton has negative charge. Where an electron has a negative charge, a positron has a positive charge. Actually, one of my kids thinks we should have called electrons negatrons. I agree. An anti-helium atom would have to have 2 antiprotons and 2 anti-electrons or 2 positrons. Classically, the antiproton is too heavy. The antiproton would have a negative charge, so it could get attracted to protons. So if you had an anti-helium nucleus and an ordinary helium nucleus, they would come together and collide and annihilate each other. But an experiment recently discovered that this doesn't always have to be the case. Now, how researchers discovered it relied on the property that we've described on this channel before. We've discussed how every element has a chemical fingerprint, its spectral bands.
Library of light, here's the different chemical signatures.
The spectrum of colors reveals the chemical composition, what it's made of, its elemental constituents, including how many protons and electrons it has. The light produced from a spectrum can either be produced, emitted, or absorbed, and each one gives a unique chemical assay or fingerprint of what the composition is. Now, the particles in helium are incredibly chaotic when normal pressure in, say, a balloon that you get for a birthday party. And so they're always transferring energy, colliding with each other, these atoms, and that causes the spectrum to get more blurry. It's harder to resolve the distinct chemical fingerprints themselves when you have a higher temperature, say a room temperature gas. So if you want to learn more about the spectrum, you might want to cool down the atoms to low temperatures, such that the Doppler broadening or the collisional broadening is lessened in effect. Now, helium, in addition to being the main ingredient for the Macy's Thanksgiving Day parade balloons, is also a gas that's called a noble gas. It is highly inert, doesn't react with itself or other molecules. Helium also has a very special property called superfluidity, which is the fluid flow analogy of a superconductor. A superconductor, when cooled below its critical temperature, has 0 resistance, as I showed when I did this experiment as shown here in my cosmology class. But what happens when you cool down helium to the point of becoming a liquid? it will flow with zero viscosity or resistance to fluid flow, similar to the way that a superconductor will have zero resistance when cooled below its critical temperature. That will make the spectral lines incredibly sharp. But recently, researchers at CERN in Geneva found that by firing antiprotons into the mix of cold helium atoms, that they replaced some of the helium's electrons with the negatively charged antiproton. They were able to stabilize this kind of hybrid of ordinary nuclei of helium-4 as it's known, with replaced electrons that were antiparticles of the proton, so that charge was conserved. You had two positive charges, the two protons, two negative charges for the two antiprotons. Antiprotons are the negatively charged analog, twins if you like, evil twins of protons. So an antiproton can take on the charge properties of an electron orbiting around the helium nucleus. In 2013, Sauter was working on an experiment on antimatter. The group assembled a hybrid antimatter-matter atoms by firing the antiprotons into liquid helium. The result was a small cohort of antiprotonic helium atoms. Cool sounding name for a fascinating type of new material. But how could it be? Wouldn't the protons eventually suck in the antiprotons? How could you get them to capture each other? This could not be explained immediately, why the helium was so well behaved.
Okay.
So the researchers had to explain why when they added antimatter protons into a bath of helium with its ordinary matter protons, that rather than annihilating each other, they instead saw the helium becoming more ordered, less collisionally broadened spectral lines, and this became more well-behaved, if you will. So let's break it down further. It was obvious that something was preventing the helium atoms from imploding on each other. But what could that be? There were two explanations for this. Either the hybrid matter-antimatter helium atoms went through a state of liquid to become what's called a superfluid, or the heavy antiprotons themselves were more orderly behaved than the electrons would be that they were replacing. They were heavier, so there would be less intrinsic kinetic momentum from a proton moving with its much more ponderous momentum than the tiny little electrons. Now again, superfluids are fluids that flow with no viscosity. Viscosity being the tendency of fluids to cling on to themselves and their containers, and in so doing, use up a bunch of energy without actually flowing smoothly. More viscosity means it flows less. Think of cold maple syrup versus hot boiling water. So what happens when you reach zero viscosity? And you can get behavior associated with individual particles, really quantum behavior, but on a macroscopic scale that ordinarily couldn't happen at normal temperatures. In superfluidity, you get these strange-looking phase diagrams, and the fluid flows without resistance, and it can actually leave and escape a container that it's in, almost as if it has a mind of its own. So even in a gravitational field, the fluid can float right out of its container. In the CERN experiment, the hybrid helium was already cooled to the point of being a superfluid. So one explanation for what happened in this experiment was that the orderly movement of superfluid helium somehow stopped it from colliding with itself, and thus minimized the amount of antimatter-matter collisions. This both caused the lack of annihilation between matter and antimatter, but also allowed the spectral lines to be incredibly sharp, well-defined, and clean, as the researchers observed it to be. Another theory is that the antiprotons are simply more orderly than the electrons they replaced. As you know, electrons are incredibly small. They're the second lowest mass elementary particle after the ghostly neutrinos that may even have zero mass for some of the three flavors of neutrinos. The electrons only have 0.5 MeV of energy, using Einstein's famous E equals mc squared scale to weigh them. The electron's energy is so small that we measure its rest mass in energy. The mass of the electron is almost 2,000 times lower than the mass of the proton or the antiproton. In hybrid helium, researchers made one antiproton and one electron orbiting the nucleus. So again, the net charge was zero. The two protons in the nucleus and the antiproton and the electron, both with negative charges, cancel out the positive charges. So a possibility for the hybrid helium being so well behaved is that in liquid form, the heavier antiprotons settle in, behind the outermost electrons in the orbital shells of helium. They mask the charge of the nucleus, but they contribute less to the interaction rate between an antiprotonic form of helium with ordinary non-antiprotonic or just ordinary helium-4 atoms. These antiprotonic helium atoms much more well-behaved than typical helium atoms. So now when I want to discipline my kids, all I have to say is, can't you behave more like your antiprotonic twin? We don't exactly know which one of these explanations is the right one. Maybe it's some hybrid of both of them, or maybe it's neither one. Researchers are still looking for the answer as we speak. But one thing's for sure, hybrid helium atom stability means that we can get more accurate measurements, a lot better spectroscopy involving materials that are otherwise too disordered and chaotic to work with. By studying extreme matter, we learn about not only ordinary matter in normal circumstances, but we may also learn about the origin and mass mechanism of how the universe has the structure that it does. Because according to symmetry principles, the early universe should have produced just as much matter as antimatter, therefore annihilating itself in the very first few nanoseconds after matter or antimatter came into existence. So we shouldn't even be here.
I'm not even supposed to be here today!
To ask the question about why it exists or not. So it's a great mystery. The matter-antimatter asymmetry relies on something called baryogenesis, which we'll talk about in future videos. But one thing's for sure, studying the properties of the smallest constituents in the universe tells us about the grandest cosmic scales possible. This investigation, using tools of spectroscopy and low-temperature physics, tells us about Big Bang nucleosynthesis, formerly solely the purview of astronomers and cosmologists working on early universe physics. Now, we won't be able to do this with any type of atom. For one thing, helium is a noble gas, as I said, and it can form a superfluid. Not all gases can do that. And not all of them can be fired at with antiprotons to form the simplest possible specimens to study. So up until now, we've made do with these blurry spectroscopic images, and we have done the best we can, but now physicists at CERN can look in a clean environment to get more and more accurate data and hopefully unveil the cosmic mystery of how matter predominated over antimatter, and how we didn't all end up as a bath of photons percolating through an empty universe. Physicists may be able to construct all sorts of novel materials. Imagine decades from now, we have an anti-periodic table created by techniques and studied by technology such as that discussed in today's video. We may even someday be able to do something with the exotic particles that are rarely discussed, the pions, kaons, and other exotic quark-antiquark combinations. Maybe they have some hidden importance that astronomers, physicists, and engineers are only just now beginning to scratch the surface of. So if you like learning about these fascinating new breakthroughs in experimental physics, cosmology, and particle physics, subscribe to the channel and click on this playlist that I made just for you. Don't forget to subscribe.